Alright, welcome back. We are very close to the conclusion. We are picking up in our seamless transition from the fundamental theorem of calculus part 1, where we established that we can use antiderivatives to compute definite integrals, and part 2, which is the converse, and says we can use definite integrals to construct antiderivatives. Now, this process of integration, okay, what we're really doing, right, is we have like some, let's say, some arbitrary function x squared from 0 to 5, right? We're looking for this area here, right? When we take the integral, we essentially come up with a new function, okay? And that function is seemingly acting as though it's a calculator, and will give us the area for whatever interval we want beneath the curve. So what does that look like as an integral? Well, we're going to have some left bound, that's a numerical value, but our right bound will be a function. Typically we see an x, but we should just treat it as a function of x. Of the curve that we are working with. Since the upward bound is a function rather than a defined numerical value, this forces the integral to become a function, because it is acting not as a numerical value but as a variable, right? And this is going to equate to the signed area from a to x, obviously with x being some arbitrary unknown value. So if we were to erase this, so I give you a little bit of a better diagram. So we had some function a x, and so here's a, here's x. Okay. The antiderivative is our area function, right? Because this essentially becomes like a slider, right? If I want to push it further, right, this is going to just be, well, once you decide on what a value for x is, boom, we can substitute it in and tell us what the area beneath the curve is for that particular integral. Let's take a look at one before we formally define the fundamental theorem of calculus part 2. So let's say we have find a formula for the area function a of x equals integral from 3 to x of t squared dt. We know that f of t is t squared. So capital F of t, right, its antiderivative is t cubed over 3. We can now apply fundamental theorem of calculus part 1, right, which says take your bounds, take their difference as they're substituted in. So the integral, or the definite integral, from 3 to x of t squared dt is equal to the upper bound in the antiderivative minus the lower bound in the antiderivative. So we'll wind up with x cubed over 3 minus 3 cubed over 3, which is x cubed over 3 minus 9. Okay. And this represents this function calculator for the area beneath this parabolic function with an interval from 3 to some arbitrary point value x. Grab my black marker. So the formal definition for the fundamental theorem of calculus part 2 says that assume that f of x is continuous on an open interval I, and let a be an element of I, then the area function a of x equals the interval from a to x of f of t dt is an antiderivative on f of x, antiderivative of f of x on I. Okay, so the area function, this is an antiderivative, right? This entire piece. So what that means, here's the big kicker, right? If this entire equation is an antiderivative, if I derive the area function, I'll get back f of x. Equivalently, if I take the derivative from a to x of f of t dt, and this, ladies and gentlemen, is the big hurrah. This idea that derivatives and integrations are not, I wouldn't say operations, but inverse concepts, okay, that naturally undo each other and leave us with our function as, or our function in terms of x. So, what does this look like if we were to embrace, a problem? Let's take a look. Find the derivative. Here's a dead giveaway of a of x equals the interval from 2 to x 1 plus t cubed dt, and then we want to calculate what a prime of 2 is, what a prime of 3 is, and what a of 2 is. Okay. So notice, yes, we have an integral that's being defined as an area function, and we're tasked with finding its derivative. So, are we necessarily integrating? Not really. Remember, okay, I'm going to derive the left side. Right, the derivative of a of x is a prime of x. I need to derive the right side, so d dx of this definite integral. But FTC part 2 says that this is really just equal to the function in terms of x. So a prime of x is nothing more than this. And we can now substitute in our values. Right, 2 cubed is 8, so square root of 9 is 3. 3 cubed is 27, square root of 28, square root of 28. And then this value gets substituted in back here. But you should notice that if the bounds are identical, the area is just 0, right? We don't have actually any width between our rectangles. So what is the FTC part 2 really saying? It's just, once again, let me reiterate that derivatives and integrations are inverse concepts. Let's just talk about this conceptually real quick. Okay. FTC part 2. We start with a continuous function f of x, and then we make ourselves form an integral, and from there we return the original function through differentiation. So we have f of x that we integrate from a to x, that when we derive said function, we get back the original function. Okay, that's FTC part 2, our little cause and effect, domino effect. Now part 1 is kind of like the best part about having a whiteboard. Well, you have to write more notes. I can just kind of piecemeal it. Okay. Well, I kind of can. Man, that's annoying. Look, my word just backfired on me. With part 1, we want to differentiate first. Then integrate. Which allows us to recover the original function only up to a constant, though, right? Because we don't actually know what that lower bound is the way we do with fundamental theorem of calculus part 2. So remember, we differentiate and wind up with f prime of x, and then we integrate the derivative, and we're left back with the original function minus the lower bound. But like I mentioned earlier in this video, with the fundamental theorem of calculus, okay, rather than think of this upper bound as x, but as a function of x, okay, aside from it being x, our derivative is going to be slightly unusual. And here's why. Let's take a look at this scenario. Let's say we have this area function, right? Compute the derivative of this area function. -2 x squared of sine of t dt. Okay. First off, this isn't even really written correctly, okay? Because here our input is x, but our upper bound is x squared. This should really say that our input is x squared. Okay. So previously, when we derived a of x, right, that becomes a prime of x times the derivative of x, which is just 1. Once again, this assumption that we've taken for granted. However, when we go to derive this function, we have a prime of x squared times 2x. So that, in itself, means that when we go to derive this, so let me write that in red. we get back the function composed with the upper bound. But what we forgot to take into account was this piece. Right, so we want to offer equality. Now, what we can do, rather than assume this automatic substitution, is we can redefine these functions. So, let's say that we had really written this as g of x was equal to a of x squared, which was equal to -2 to x sine of t dt, right? So this allows us to go back to how the fundamental theorem of calculus is really built. The method in which I just demonstrated is more of like an experienced route. But if we're tasked with deriving, right, we take the derivative of g, which is g prime of x, right? And so we derive that, as I said before. We must remember to derive the inner function, right? And then this piece now falls under the fundamental theorem of calculus part 2 and leaves us with this, right? So g prime of x is equal to sine of x. Okay? However, we need to make sure that we compose or we insert our original input, so sine of x squared, while remembering to account for that because of the chain rule. So if we wanted to write this out, remember when your area function is defined with an upper limit or an upper bound that is a function not x, we should really rewrite the area function using a composition of functions where this composition of functions, where a of x, and I'll rewrite this, where a of x is then equal to the integral from a to x of f of t dt. So when we go to apply the chain rule now, on this piece, g prime of x is equal to a prime of x times, a prime of g of x, times the derivative of the inner function, which is equal to f prime of g of x, f prime, times the derivative of the inner function, right? Because we know that this, right, when we derive this, we're just going to get back the original function. So f of x, however, it was composed with a function that was not x, that was, a degree higher than x, while accounting for the fact that we'll need to apply the chain rule. Those can be a bit of a doozy. So if it was a little tense, once again, what we want to do is we want to define it first in terms of x, okay, while rewriting that upper bound as not a new function, but just a rewritten function. Thus, when we go to take the derivative of g prime of x, this is going to invoke a chain rule that we wouldn't account for here. Okay. We get back the original function, or the function in terms of x, through the fundamental theorem of calculus part 2. However, we would need to reinsert the upper bound as the input while accounting for the derivative of said input. And that'll do it for the fundamental theorem of calculus part 2. Our last video is going to be on the substitution method, and that'll wrap us up for our Calculus 1 journey. See you there.